did, 2011 to 14, saved 19 megawatts with a 30% IRR. Just re-engineering the chiller plant saved 30% energy, 45% equipment cost, 25% space, 2.5-year payback. Making the roofs white on 2.5 lakh square meters paid back in 2 years. And yet the official projections hardly include retrofits. Now, such efficiency does require unreasonably ambitious but severely practical goals, strong leadership, innovative design, meticulous attention to detail, careful measurement, and data-driven operations. But just by 2030, on, say, 10 billion square feet of new commercial space, you could save at least 45 gigawatts of peak demand. By the way, they do equally impressive things with water and waste efficiency. Now, to encourage developers, how can you get this done? Well, government could raise or lower the floor area ratio based on the measured efficiency of your previous building. Or, to connect a new building or major renovation to the grid and other public services, you could pay a fee or get a rebate, which and how big depending on how efficiently the building uses those services. Fees pay for the rebates. You notice building standards are obsolete before the ink is dry, and they give no incentive to do better, but such fee-bates drive continuous improvement. Design professionals perform much better if you pay them for savings, not expenditures. Performance-based design fees. Government could procure design in this way. Local government could simply allow all super efficient new buildings to go to the head of the queue for any required approval. This costs government nothing, but to a developer, time is money. And of course, buildings could be labeled with their measured efficiency, just like restaurant health inspections. I saw such a label in the Niti Aayog building today, but I'd like to see a lot more of them. And they should be mandatory so that the market will start to recognize which buildings will be cheaper to work in. Now, what about households? Modern Book of Buildings are seldom as climate responsive as the Indian standards invite. Niti Aayog's forecasting tool says the 2047 residential cooling loads will differ only about 17% between slight and heroic adoption of improved building envelopes, so clearly the improvements must be pretty modest. But a design as sophisticatedly simple as Dirur Thandani's convectively vented double wall sustains 6 to 12 Celsius degrees of passive cooling at an extra cost about 2%. By the way, it keeps the inner wall dry and mold-free through the monsoon. So the 2 million square feet he did just before 2000 were very popular. Karan Grover, architect I dined with the other night, routinely achieves 11 Celsius degrees passive cooling by other methods. And if you have proper 3 or 3.5 meter ceiling height and put in a good fan, you get another 5 Celsius of comfort range. And airtight fiberglass casements, windows coated to block heat, better interior cross ventilation, and you have pretty good comfort. And of course, our teacher in all of this is the millennia of passive design experience that can provide surprising comfort even in kacha houses. I've been in some that give astonishing monsoonal or pre-monsoonal comfort, and we've known for thousands of years how to do this. We just forgot. Moreover, the best new air conditioners officially assumed for 2047 are only half as efficient as the best on today's market. Of the 150 gigawatts of new peak load expected from urban households aircon by 2030, modern and well-enforced efficiency standards could easily save at least 40 gigawatts, and then a factory-installed smart chip could make the rest of the 150 gigawatts dispatchable. Huge demand response opportunity. Finance it on bill like your excellent bulk purchased LEDs. And this huge demand response is actually so valuable that smart, super efficient aircon units may be worth giving away as a resource to the grid. Now, other household uses. Today's best market technologies can cost effectively make ceiling fans over twice as efficient as the Indian norm, refrigerators 7-fold, television 6-fold. Samsung's latest TV uses 10 watts. It's a very nice 22-inch color unit. So that permits a home package that's now on display at the U.S. Embassy in Delhi of this nice color television, 4 LED lamps, a radio, and a mobile phone charger, drawing 18 watts total. You run it all off a 27-watt photovoltaic. The total system investments, supply and demand side, is half normal. So with ambitious and ratcheting efficiency standards like Japan's Top Runner program, you could greatly accelerate energy access. You could give India a lead in the global export market for super efficient appliances, and you could avoid just in the top 10 household uses about 100 gigawatts of new supply. Agricultural pumping. 90% of India's water withdrawals, $10 billion a year in subsidies. The 1.8 crore electric irrigation pumps use about 19% of India's electricity. They have a connected load officially 100 gigawatts. It's probably about 150 in fact. Say 50,000 feeders, each 3 megawatts. And the pumps are generally inefficient. They're poorly controlled. They run on free or subsidized power to deliver water, 2/3 pumped from groundwater, most of it wasted. Big problem. Among the 9.3 crore smallholders growing over half the farm output, even those on the grid are often power deprived. And when you start tracing through the causalities, I think the inefficient irrigation, straining grid capacity, limiting new connections, encouraging theft, worsened by theft, starves the discoms for revenue. It's one of the major sources of the financial distress in the discoms. Of course, diesel pumping is worse. Devours 60% of farm income, $3 billion a year in foreign exchange, limits farmers' profits. Now, some Indian entrepreneurs are offering a compelling value proposition. Sometimes they integrate with the upwards of 4 telecom towers. And some of the new business models double or triple motor pump system efficiency and then dispatch demand response and surplus power back to the grid. So the farmer is a solar farmer producing a lot of extra revenue. And over time, this can halve the cost of serving ag customers so the discom can reinvest in greater access and more connections. The state saves half its cost. The farmer needn't contribute but pays a rational tariff, maybe 4 rupees for actual usage. The developer invests the capital in the pumping and control infrastructure as well as the PV. The grid's better utilized. And then you can save even more cost by reducing pipe friction, bundling solar pumping with drip irrigation, which is still under 5%. But almost all of it is actually at about 10 times the pressure that smallholders need. So that, again, is wasting energy, wasting materials in heavier pipe. A 1 meter head is fine for a 1 or 2 meter smallholder. And drip can also shrink the PV system to irrigate a hectare from groundwater in the suction range from 2 kilowatts down to 600 watts, already demonstrated in Gujarat, and probably to 400 watts, which gives the smallholder a 1-year payback on the whole system. Of course, then you can save even more water with cheap root zone moisture controls that measure and supply just the water the plant needs. And then the electricity to crop efficiency ratio ends up probably over twice the 37% assumed in the best case of the official forecast. And then if farmers diversify from, say, wheat to high-value off-season fruits, spices, vegetables, and even add more value like distilling mint oil instead of selling mint leaves, their profits can rise hugely. But even with standard crops, some practitioners of radical efficiency in irrigation are offering smallholders 1 or 2 year paybacks today, and they can pay for the whole system by immediately quintupling the yield of associated fish ponds. Now, perhaps, here's my policy dream, a government revolving fund could progressively substitute such systems finance for the existing irrigation energy subsidies. So you phase the efficiency in, the subsidy out, and solve all of these problems at once. Now, motors are India's biggest user of electricity. They use about 3/5 of the world's electricity, and almost every motor system can be profitably greatly improved, even the big ones. The most comprehensive analysis of this opportunity, which I led 20 years ago, found 35 motor system opportunities between the meter and the input shaft of the driven machine. And if you buy the correct 7 savings first, you get 28 more as free byproducts, and you save about 3 times more electricity at a fifth the unit cost compared to standard forecasts. 2 improvements, just more efficient motors run at variable speed. Pumps and fans use about half of motor power, and they offer dramatic further savings I'll mention later. And lastly, an example of high-tech industries. We design a lot of data centers, chip fabs, and so on. So let me give you a data center example. If you feed 100 watts of coal into the power plant, maybe a third of that gets to the meter. Of that, maybe half gets to the server. The rest is wasted in the cooling systems and uninterruptible power supplies that are half the capex of the data center. And then of what gets to the server, maybe half gets to the chips, the rest being wasted in terrible power supplies at part load and a lot of big fans to take heat that shouldn't be there into the room where we can do dumb things with it. Then, of course, the computing resources are often greatly underutilized. So this little stalk coming out the lower right is so small it's about to vanish. Let's magnify it. Next problem is bloatware. There are a lot of threads and processes going on that we don't really want or need. And we may even have inefficient business processes downstream of that. So in such a series of compounding losses, you should always start the savings downstream. So let's first write elegantly terse code. Indians are very good at that. So that every compute cycle is a needed and wanted one. I had assumed originally this might save a factor 10 or so. It actually saves about a factor 100 in the latest tests. And that's how bad the bloatware is. Then we can make the servers at least 4 times more efficient, more nowadays. Then they don't need much cooling or power supply, and there are much better ways to do those. And then we can even get rid of half the utility loss with fuel cell trigeneration. So when you multiply all the savings, there's a 2 order of magnitude potential here. And in fact, the best data center we designed, we were told, had all our recommendations been adopted by the client that EDS thought were a good idea, would have saved about 95% of the energy and half the capex. They didn't actually adopt most of them, so we only were able to triple the efficiency at the same capex. But there's a lot more on the table.